All right, so we're looking at section 3.1 today, solving systems using graphs. Shouldn't be too bad. I mean, as long as you can graph lines. I mean, we're just going to graph lines, see if they cross. If they do cross, remember our solution is going to be that point of intersection. So that's our goal today, just to solve by graphing, but we're going to talk about some vocabulary or some ways to classify systems of equations, because really why we start with graphing is just so you can kind of get a visual picture in your head. So when you're solving systems of equations, you can kind of see why or what's happening if you were to graph those two lines. But the systems of equations, just to kind of recall, is where you have a collection of two or more equations with the same variables. Solutions of the equations are the variable values that make every equation true. So and when we look at it graphically, it's really going to be where they overlap or where they cross. But some definitions. So we say that a system of equations is consistent if you have one or more solutions. I'm just going to abbreviate solutions, SOLN, so I mean solutions. Independent is where you have exactly one solution. Sorry, this is, so exactly one solution. And then dependent is where you have infinitely many solutions. Here, let me actually see if I can just type these in. So consistent is one or more. Okay, independent is exactly one. Solution. Okay, and then dependent is where you have infinitely many solutions. And what does that look like with lines? That means basically they're the same line. So like they overlap everywhere because they're the same exact line. Okay, so those are some terminology. So consistent means you have one or more solutions. So really what that means for consistent, we're going to kind of look at this quick, but that means you either have like lines that cross at one point, or you really just have the same line like that overlaps exactly the same way. So it's touching everywhere basically. Independent would just be like that, what I have in red, like where they cross at one spot. And we'll have one thing I forgot to put here is, sorry, we say it's inconsistent if it doesn't cross, or if they have no solutions. So basically that means they're parallel lines. Sorry, here, let me type, because my handwriting is so bad. So sorry, one thing to add to this top part, sorry, I forgot to put a spot for it. Inconsistent lines are like where you have no solutions, or AKA they're parallel lines. Thank you for fixing. So if you want to add that, if you are writing this down. So let's just look at a few examples and we'll kind of talk about these terminology. But one thing I'm going to have you do in our systems unit when we get more into these sometimes is just have you classify like what type you have. Is your systems of equations, is it consistent? Is it independent? Is it dependent? So just kind of understand what these terms mean. So we're going to just kind of do quick two examples here quickly. If you don't have graphs, I mean, you can kind of just look at it. But for this first system, and I'm just going to do a rough sketch. So that first line, if I graph it, it would start down at -5. And the slope of it was 2, so it would go up 2/1. I can do this kind of neat. One thing with systems of equations, it's usually a good idea to put as many points as you can. I'm just going up 2 over 1. And if I want to go the opposite direction, you go down to the left one. Okay, so that should be plenty. Oops. Like something roughly like that. For my second line, I'll do it in red. So it starts up at 6. And it goes down 1 over 1. And you would, oh, it should actually cross here, did I? I think it's actually like a fraction or decimal. We're not really worried on the true solution, but if I did that right, it didn't look like it crossed at a nice point actually. Like where they both had a point. So I could be wrong about that, but just so you can see, this is an example where they intersect at one point. So we would say that it's consistent because it has at least one solution. And we would say that it's independent because it also has exactly one solution. Really, what's unique about an example that looks like this is it's independent because this one has one solution. One thing about the slope or y-intercepts, they should have different slopes because that's why they cross. If you have the same slope, obviously they're parallel, they won't cross. So they have different slopes. And they should, well, I guess in theory, the y-intercept doesn't really matter. They could, in theory, have the same y-intercept. That could be the point that they intersect. So I'm not going to put anything about the y-intercepts because it depends on the question. Is really, they could be the same, they could be different. It doesn't for this situation. No solution is if you graph and you get 2 parallel lines. So if you graph these, like I said, I'm just going to do a really rough sketch. It would start up at 5. And our slope's up 2 over 3. So I'm not even going to put a lot of points because I already know it's going to be parallel. So then if I graph the second one, I'll do that one in blue. It would start down at -3, go up 2 over 3, look like this. But if you ever have parallel lines, we would say that it's inconsistent because there's no solution. Like this one, our solution's where they cross. So the thing about parallel lines, obviously they have to have the same slope, but different y-intercepts. Because if they had the same y-intercept, they'd be actually the same line. For this one, if you solve this equation just for sake of time, but if you, well, I mean, all you're going to do is divide by 3. But you would see it's actually the same equation. So a lot of times they give you things in different forms, so you might not realize it's the same line. But if you graph it, obviously, those are just the same equations. So our line would look like this. And if you graph the other one, let's say I graphed in red, I mean, it's just going to overlap. I was kind of sloppy with going through that point. I completely missed. But for right now, I mean, I'm just trying to give you an example of each. So we would say that this is dependent because it's the same exact line and it has everything's the same. So same slope / y-intercept. So these are the 3 things that can happen when you solve the systems of equation. You can get one solution, which would make it, which we would classify as independent. You can get parallel lines, which we call inconsistent, or you could get the same line, which we call dependent. Technically, since remember, consistent just means it has one or more solutions. The first 3 examples are consistent, but since the parallel one doesn't have any solutions, it's inconsistent, is what we call it. So usually consistent's not really a label we use to be specific because it can mean more than one case, but independent, inconsistent, and dependent are unique to these 3 examples based on those definitions up here. So for example, if you ever saw a question where I asked you to classify a system of equations, you'd kind of either want to solve, like get them all y equals, and you could just look at them. You could look at like their slopes and stuff to see which case it is. Or you could quickly graph them or make like a quick sketch and see. So if you have, they're just crossing at one spot, well, you would say that's independent. If they're parallel lines, you would say they're inconsistent. If they're the same line, you would say they're dependent. So one thing to think about, is it possible to identify solutions clearly by graphing for all systems of equations? Well, no. I mean, the reason solving by graphing isn't used for every problem is a lot of times you get decimals, or you get places where they cross that aren't super nice. Like, for example, I'm pretty sure, unless I was just sloppy, this one would be an example where it's hard to see exactly where they cross, but it could have just been me being sloppy as well. But if you ever get decimals or fraction answers, it's hard to get an exact answer from graphing. I mean, it can give you a good idea or a good approximation, but if you want to get an exact answer, that's when we'll use those algebraic methods like elimination or substitution, if you remember doing those in Algebra 1. So I just want to look at a few examples, and we'll kind of wrap up class then. So looking at example 1, the first thing you always want to do, unless you want to graph it based on the form it is, but it's probably easiest because you're most familiar, just to get them in slope-intercept form. So for example, this second equation, like the first thing I would do is just solve for y. So I'm just going to recopy it. So you would just subtract the x over. So you would have 3y equals negative x plus 27, because you can't combine those. If you divide, you'll have y equals negative 1/3 x plus 9. So if you graph this, I'll graph the first one like here in red. So we'd start down at -5. My slope's 2/1, so go up 2/1, up 2/1. Should be plenty. If I need more points, I'll just put them in. And then for the second line, I'll do in blue. So it starts at 9, and our slope's negative 1/3. Down 1/3, down 1/3, down 1/3. Crap, I think I regret not putting more points. There, let's just add some more. I think this one should have a nice answer. Up 2/1. Yeah, I got sloppy. Yeah, this red line should have actually went like this. Oh no. But you should see it crosses it at 1, 2, 3, 4, 5, 6. And it crosses up 1, 2, 3, 4, 5, 6, 7. So our answer would be at the point 6, 7. So we only have one solution because they're not the same line. You're only going to have one if they cross. I was going to have you guys check these with your graphing calculator, but we will worry about that at another time. So that's our first one. So this would be in, if we were classifying it, since this just crossed that one spot, we would say that this is an independent system, like, because it has one solution exactly. So this is independent if you were to classify it. All right, for this next one, we'll just graph the first one. We'll solve for the second one, just for the sake of time. If you did solve or get y by itself in this equation, you should just get y equals positive 1/2 x plus 4. So if we sketch these, I'll do this one in blue. I'll do this one in red. So -5. I mean, one thing to notice, they have the same slope, but different y-intercept. So they're going to be parallel lines. So I'm not going to put a ton, like, since I know they're parallel, I'm not like really on the lookout for where they cross. So 1, 2, 3, 4, 5. And then the other one starts up at 4. Goes up 1/2. And there's no solution because they don't cross. And if we were going to classify, we would say that this system is inconsistent because they don't intersect or have any solutions. For our last one, and this one will require a little bit more solving. How do we do it on time? Maybe I'll actually do this one. So you'd have y plus 7. You could distribute the right-hand side. Then you would subtract that 7. And then for the bottom one, pretty simple, just subtract the 3x over. So you would just have this. Sorry, I'm going a little bit fast. Oh wait, did I mess something up? Yeah, I did. Sorry, this should have actually, was going fast. This should have been -3 times -1. This should have been a +3. So then when you subtract it, that would have actually been a -4. But notice these are the same exact equations. So if I graph them, I mean, they're just going to overlap everywhere. But I would start at -4, go down 3 to the right 1. I mean, I don't really need a lot of points. Oops. Then if I graph the other one, I mean, it's just going to do the same exact thing. So if you ever have like an overlapping equation, what's your solution? It's really, there's infinitely many. Like any point on those two lines is the solution. So since the lines go on forever, there's really infinitely many solutions. And since they overlap, we call that, based on our terms from the first page of our notes, remember that is a dependent system of equations because they have an infinite amount of solutions. So if you ever do because eventually when we have like our quiz or test over this, I'll probably give you a couple questions where I ask you to classify a system of equations. That's what I mean. So if it has like one solution, we call it independent. If it has no solutions, we call it inconsistent. And then if it's the same line or really infinitely many solution, it's dependent. And we'll see when we're solving systems of equations, like how you know. I mean, obviously, if you get your answer, it's independent. And most of the problems you kind of come across, usually they're independent because they kind of give you problems that usually have solutions. But we'll kind of see what it looks like algebraically if you have no solutions, or what it looks like when you have infinitely many, probably tomorrow or Wednesday, depending on kind of how